Hello and welcome to lesson 6, which is on the ideal gas law. So this lesson we are going to take the preceding 3 lessons and we're going to put them all together into one combined idea to express gases using one mathematical idea. It's really important that you've understood the previous 3 lessons. So if you haven't, I recommend stopping this video now and recapping those lessons. Once you're happy, you understand, then we can continue with today's lesson. So the first activity I would like you to complete is to complete 3 questions on this slide. So pause the video now and on paper answer these 3 questions. Okay. You should recognize these 3 graphs as 3 graphs from the previous 3 lessons. So you should have these 3 graphs drawn. So volume is directly proportional to temperature if temperature is in Kelvin. If temperature is not in Kelvin, then the line should look like this. Pressure is inversely proportional to volume. Importantly, it does not touch the axes. This will not touch because this is what inversely proportional means. If it was to touch the axis, it wouldn't be inversely proportional. Finally, pressure is proportional to temperature, again, as long as that temperature is in Kelvin. If it's not in Kelvin, the line will look like this. You should remember that the middle one here is Boyle's law. This one is the pressure law or gauge law. We're going to write some mathematical expressions. The volume divided by the is equal to a different volume. That's what directly proportional means. If one thing doubles, the other thing doubles. Or if one thing halves, the other thing halves. The first pressure and the first volume is equal to the second pressure times the second volume, because that's just what inversely proportional means. If you times pressure times volume, you'll get a constant. And then finally, here, this one is the same as the first one, but obviously we replace the volume with the pressure. So these 3 ideas are extremely important, and hopefully it was very easy for you to answer these. So let's move on to ideal gases. So we're going to obviously look at gases, clues in the title, but we're going to look at ideal gases. What does ideal mean? Well, it basically means we are going to look at the model gas, or like a perfect version of a gas. We're going to make some simplifying assumptions so that we can mathematically model the gas in an easy way. So what I'd encourage you to do now is to rewind the video 30 seconds, mute it, watch this animation, and think about what assumptions we might need to make in order to model this gas. So what thing you need to assume about this gas in order to make the maths easy. Pause the video now and think about that question. Okay, not necessarily easy. I wouldn't expect anyone to be able to get everything, but it's useful for you to think through how you might actually approach simplify it. So let's look at some of the assumptions. Now, obviously, I've already made this clear, but it's worth really stating that real gases do behave differently, especially those that consist of molecules in almost every single gas in the real world. So we are making assumptions, and it's not perfect, but it's pretty good for most situations, or a lot of situations. So the most important assumptions is that it's monoatomic. So helium, for example, is monoatomic. Most gases aren't. Oxygen, nitrogen are not monoatomic, they're diatomic. In reality, oxygen, nitrogen fairly well as an ideal gas, but it's not perfect because they're not monoatomic. Now, there are reasons for this. And if you think of the structure of a monoatomic gas compared to a diatomic, and think about the ways they can move, there is a difference there. Something that's diatomic can spin in different that a monoatomic gas can't, and that really does become important later on. It's a little bit beyond the A level, but we will touch upon it. So there are subtleties as to why that is important. Secondly, we're assuming it's not at a very low temperature. So what I mean by that is not absolute zero. We're going to assume, room temperature, minus 50 degrees, 100 degrees, 600 degrees, something like that, but not at the very, very, very low temperatures near to absolute zero. We're also going to assume it's not at very high pressure. Now, this is obviously relative and quite vague. I can't give you an exact figure for this, but we're talking about an atmosphere, a few atmospheres. We're not talking about, hundreds of thousands of atmospheres. We're not talking about the pressures that mean the gases turn into liquids. We're talking about pressures where the gas is still a gas. This is an important one. We assume there are no interactions between molecules except during collision. Means there are no forces between the molecules, which might arise because they're charged or because of dispersion forces or van der Waals or dipoles or whatever else you want to talk about in terms of the chemistry. Only interaction is that collision, so an actual contact force when two atoms collide into each other. What that therefore means is that collisions are perfectly elastic. Elastic means all the kinetic energy is conserved. So whatever speed they start at, that's the speed they end at, but they're obviously moving in a different direction. There is no energy lost as heat, no energy lost any other way. There's a few assumptions we're going to go look at in the next slide, but I'll go over these relatively quickly. I would encourage you to pause the video and read through this list now. So the first two on this list are relatively simple. It's just trying to encourage you to think in terms of large numbers, because if you just pick one gas molecule or two gas molecules, that's obviously not going to behave the same as billions or trillions. The third point on here really follows from something on the previous slide, that the only force we care about is in collisions. The fourth point really follows from that as well. So does the fifth point. And the sixth point is kind of linked with the first two as well. Now, we're going to come back to these next lesson when we look at the kinetic theory of gas. I don't want to say anything more about that. Some of them follow from the previous slides, and some of them are just due to the way that we model gases. So let's move on. Oh, and finally this one, which follows from point number 4 on point side. So pause the video, spend 10 seconds to read over this. Something I've already said, that we're making simplifying assumptions, but importantly, most gases can be modeled very well. So if you take the air in your room right now, you can apply the equations of ideal gases to that room, and you'll get a pretty good answer. So we're going to work with something that's useful. You can look up other ways of modeling gases on Wikipedia, for example, and you'll see that actually they're quite similar to the ideal gas equation. They just kind of contain little corrective terms. So it's not like I'm teaching something that's completely wrong here. Now, before we start, we need to obviously understand a couple of extra little things. Firstly, we need to be happy with the idea of a mole. So two things I want you to do. I want you to pause the video and read through this poster. And I want you to open the link or type that link into your browser, read the article that's in that link here. So hopefully from the article, although more so than this picture, a little bit silly, you will have remembered, if you don't already, that a mole is just a unit of measurement. It's just a big number that becomes a useful measurement when we're doing chemistry, when we're talking about a large number of things. So we used to say the mole was the particles of a substance as there are in 12 grams of carbon-12. So there were about 6 times 10 to the 23 in 12 grams of carbon 12, and that used to be defined as a mole. Carbon 12 was used because it's common, it's fairly easy to work with in this case. It's fairly relatively pure in terms of the isotopes. However, as of last year, the mole was something that was redefined. Avogadro's constant specifically was something that was redefined, just like the kilogram was redefined. And actually, the mole had to be redefined as a result of the kilogram being redefined. So now, Avogadro's constant, which is equal to 1 mole, is defined as exactly this number. So this is the definition of Avogadro's constant, which is equal to 1 mole. Why this change happened? Search on the internet for redefinition of the kilogram. The National Physical Laboratory has some really good articles on. I'll try and remember to these in the Google Classroom. If I don't, search for the National Physical Laboratory redefinition of the kilogram, and it explains clearly why this now has been defined and is not measured. And it all comes from this one thing about the kilogram. So if I have a mole of atoms, I have this many particles. If I have a mole of oranges, I have this many particles. If I have 10 moles, I have 6 times 10 to 24 particles. Right? It's just a number. It's just like saying if I have a dozen of something, I have 12 of something. If I have 100 of something, you obviously know what that means. It's just a much bigger number because we're working with atoms and particles and molecules, which is absolutely tiny. So what are we going to do now? We're going to derive the ideal gas equation. So let's look at the first line here. So from Boyle's law, we know that volume is inversely proportional to temperature. Charles's law, volume is proportional to temperature. This third equation here, volume is proportional to the number of moles of gas. We haven't really this, but it's kind of common sense. You can think of this in terms of something that's every day. If you put a load of apples in a box, obviously the volume these apples take up proportional to the number of apples you have. You have twice the number of apples, you have twice the volume, etc. This is not really anything particularly special, it's just common sense. We'll struggle with. It depends on how confident it is. If volume is proportional to this, and volume is proportional to this, and volume is proportional to this, then it follows that volume must be proportional to all of these things combined. So if we multiply all 3 of these together, effectively, we get this. And I'm saying volume is proportional to all of these. So now we want to turn this into an equality. So we need to add a constant. So volume is some constant times NT over P. And then we can rearrange to the usual form that we see this in. There's nothing wrong with this form, but we usually see it in this form here, where we take pressure over the other side. So we get pressure times volume is, sorry, that should be an equal sign here, is equal to nRT. So this constant here has changed into R. So R is the constant here, and it tells you at the bottom of the slide, R is the ideal gas constant. It makes sense, it's for the ideal gas equation, and it has this value here, 8.31 joules per mole per Kelvin, and this is given to you on the data sheet. So pressure times volume is equal to the number of moles in a gas times by the ideal gas constant times by the temperature of that gas. And this is a remarkably good equation. You can work out the number of moles of gas in your room, for example. And you could use that to work out the density of gas in your room. I'd actually recommend you do that because it's a really nice exercise, actually, to estimate the density of gas in your room and see if you can get close to the correct value. So recommend you pause the video now, use this equation and the equation for density to work out the number of moles of gas in, so the density of gas in your room. Okay, hopefully you gave that a go. Obviously, I don't know what the volume of your room is. Pressure is going to be 1 atmosphere. Temperature is going to be, roughly 300 Kelvin. So you can plug that in and get a value for a number of moles of gas in your room. You can then obviously work out the mass of gas if you convert the number of moles into a mass, and you know what the atomic masses of nitrogen and oxygen. You could probably just assume it was nitrogen, to be fair, because it's pretty similar to oxygen anyway, and 70% of your room is nitrogen. And then you can use density as mass over volume to work out density. And you should have had it, should have got something in the region of 1.2 kilograms per meter cubed. If you got in that region, then you did a good job. And if you didn't, you might want to double check your calculations. Now, there's a little bit of an aside, but I always find that figure fascinating because we don't always think of gases as having a mass. And if you think about a meter cubed, which is a large volume, I would never think, just instinctively, there's a kilogram of air in there, but there is. We just don't notice it because it's floating effectively, and we as humans are used to the pressure of 1 atmosphere. So if you think about if you imagine lying on the floor, your surface area is probably about a meter cubed, and above you, going up to space, there is a column of air on top of you, and that is going to have an equivalent mass of 100,000 kilograms, because atmospheric pressure is 100,000 kilograms per meter cubed. So at every single moment of the day, you have a mass of 100,000 kilograms on top of you, which is insane. Because if I put that on top of you now, obviously you won't be able to cope. But obviously we're used to it. We've evolved to deal with that pressure. So that's why we don't notice it, and that's why we don't think of air as having this mass. All right, here is the equation summarized. So you can pause the video now and make notes if you want. Just to really highlight, temperature must be in Kelvin because we're dealing with proportional relationships. So you must always change temperature to Kelvin in these questions, unless it's a pure ratio question. So I'll try and highlight that a little bit later. One more piece of information. STP. STP means standard temperature and pressure. Tells you that that's when the temperature is 273 Kelvin and 1.01 times 10 to the 5 pascals. It also means that 1 mole of gas occupies 22 liters, or 0.0224 meters cubed. This is more important for chemistry, but sometimes in physics it will talk about STP. Okay, pause the video now and try this question. All right, fairly simple. This is just plugging numbers into PV equals nRT. You do, of course, have to change temperature to Kelvin because we're using that equation directly. Pressure needs to become pascals, so you do need to use a pressure of 100,000 pascals. Moles is just 2. So if we plug that in, you should get this as a volume of gas. Now, sometimes it's useful to work purely in terms of ratios. So sometimes this is a useful version of the ideal gas equation. So on the left-hand side, we have a gas at a starting pressure, volume, and temperature. And then on the right-hand side, it's changed pressure, volume, and or temperature. So you have questions like a piston of gas is compressed. It started at this pressure, this volume, this temperature. What is the final pressure, volume, and temperature after we compress the gas? And in these cases, we don't need to work in pascals. We can work in kilopascals. We don't need to work in meters cubed. We can work in liters, etc., because we are doing ratios. So these units would cancel. However, we do still need to work in Kelvin, because if we're adding on 273 to a temperature, obviously that's not going to cancel in a simple ratio. So here, temperature must still be in Kelvin. Doesn't really matter what these units are. This is also useful when you haven't been given the number of moles of gas and you're being asked to work out changes in something. Very often, one of these will be constant If one of these are constant, then hopefully you can see it just changes back into either Charles's law, Boyle's law, or the pressure law. So here's a question using that idea. Pause the video now and try this question. So hopefully it wasn't too hard. You obviously need to use this equation here. It tells you the starting pressure is this. The starting temperature is 10 degrees Celsius, which is 283 Kelvin. The starting volume is 3 liters. We can leave it as liters because we're doing a ratio. And then on the right-hand side, we have the new temperature is 293. The new pressure is this. You just need to plug in all the numbers and find out that this is the new volume. So you can see that the air in her lungs has gone from 3 liters to 9 liters, expanded by a factor of 3. Obviously, if she did that very quickly, she would be in a lot of trouble. Okay, your lungs obviously can't expand that much. Now, in reality, it's a little bit more complicated than that. Obviously, she will be able to breathe out. She wouldn't be holding her breath the whole time, so she'll be breathing out some of that air. But what this does mean is that you can develop other symptoms like the bends, where you have nitrogen bubbles in your gas, so nitrogen gas bubbles forming in your blood because of that change in pressure, and that does cause pain because the nitrogen cannot get out of your blood quick enough. So although maybe this number is a bit unrealistic, moving up that quickly is still dangerous. Okay, question 3. Pause the video and try this question. So slightly trickier, this question. You need to follow a few steps. So firstly, you need to recognize that density is mass over volume. You need to realize that volume can be expressed in terms of the ideal gas equation. So we can substitute in P over nRT. And then apologies, I think this is a mistake here. We should be looking at this one here. So now, number of moles, we're going to pick as 1, because that's nice and easy. If we pick the number of moles as 1, then the mass is just 0.045. The pressure is given to us. R is a constant, T is given to us, and it's already in Kelvin. So we plug in all those numbers and we get this number here. You can tell that's about right because the normal density of air is about 1.2 kilograms per meter cubed. We know that carbon dioxide is more dense, but obviously not ridiculously dense. So it must be a bit more than 1, but not ridiculously more than 1. So this seems pretty reasonable. It also means that carbon dioxide obviously will sink. So if I had a cup of carbon dioxide and I tipped it out, it would sink to the floor. And some of you might have seen in the news in the last month, I think it was in the last month, might be just before that, some unfortunate people in, I believe, Russia managed to kill themselves when they tipped a of dry ice into that quickly sublimed into a gas, so it became gaseous carbon dioxide. That is obviously a lot more dense than air, so it just stayed on top of the swimming pool. It didn't obviously mix into the air like any other gas would do, and that meant that the poor people in the swimming pool suffocated because all of the oxygen was displaced by carbon dioxide, which sat on the surface layer of the swimming pool, which they were in, and obviously all they then breathed in carbon dioxide and not oxygen. So that is the end of this lesson. I will obviously set you some work on the ideal gas equation. Goodbye.